All right, hi everyone, welcome to Data Systems Seminar. Today I'm very excited to introduce Helen Xu, who is here visiting us from Georgia Tech, who's an assistant professor there at Computational Science and Engineering School. And her main research interests are in parallel and cache-friendly algorithms and data structures. And today she will talk to us more about the recent advances on in-memory cache-friendly data structures. Whenever you're ready, please take it away.
Thank you for having me. Can everybody hear me okay?
Yeah.
Great. So as I said, I'm excited to be here. Thank you. And I want to just share a couple of recent things that I've been working on. So as all of you are working in data systems, you probably know that B and B plus trees are one of these classical data structures in this area. They are everywhere in indexing systems for databases, file systems, and so on. And the classical design is like this. It's like a binary tree, but rather than two pivots, or rather than two children, you have B or B plus one children, you have about B children. Where B is some parameter based on either like in memory, the cache line, similar, something like the cache line size, or on disk, something like the disk block size. But this is one of these very fundamental advancements in indexing. And the reason that we're interested in this is because of the memory system. The only reason that you would ever be interested in B trees is because of spatial locality and blocking for your pivots. And we know from theory that B trees are asymptotically optimal in some caching in the DAM model, which is a classical caching model for point operations, which are like insert and find. And there are lower bounds, like as a function of some tunable epsilon, like on one very extreme, we have logging, on some other very extreme, we have something like B trees. So it's a really nice classic result. And in the first thing that I'm going to talk about today, we studied this trade-off between insertion, between point and range operations in B trees. So in B trees, one tunable parameter is the number of bytes in the node. And here we just did some experimentation. The y-axis is normalized performance. So 1 is the best over this experiment. Close up is good. And x-axis is the number of bytes in the node. And this is just something that you can change in like any standard B tree implementation. And the three operations are this brownish line is range query. This red line is point find, and this blue line is point insert. And the way that we ran this experiment, we just set the node size and we ran a bunch of concurrent operations of this kind. And you can see that as the node size is increasing, there is first some increase in insert, and then it's dropping. And then same find is like increasing a little bit and then falling off with the node size. And range query is continuing to go up, even as the node size gets large. And so there's a trade-off. And we want to achieve good performance in both of these axes, on both point operations and on range operations. So classic trade-off in B trees. And the reason that we are interested in this trade-off is traditionally, like in the YCSB workloads, we have been interested in operating the point operations like find and insert. Even though there are range queries in YCSB, the traditional workload has very small range queries. So they're similar to point queries. And that's OLTP, like transaction processing. More recently, there has been interest in OLIP workloads, which are analytic processing workloads, and especially doing both of those types of workloads in the same data store.
Can I get into this graphing?
Yeah, of course.
First of all, the system of experiment is in memory, in space.
In memory.
In memory. And what is the intuition behind the insertion going up and down?
It's a good question. We will explore that a lot. Actually, it's really interesting. Like 2 to the 8 is like cache line.
Cache line, yes.
But you can see like it's not the best at a cache line. Indeed, it's better a little bit further. And there were studies previously that were showing this. They didn't do them concurrently, really, though. But we still found the same thing, that the jump is here, like it's still going up. We have some conjecture later on about why this is true. I think it's due to something like prefetching. It turns out like you can see that it's never the right idea to get one cache line. It's always the right idea to get at least a few. Yeah.
I mean, it makes sense also because you're gonna have some extra locality. I mean, you don't need only one cache line.
Right. Yeah. Yeah. So this is telling me that the prefetching is pretty aggressive. Yeah. And we will talk much more about this later because I think this is like the core of why we can study this, which is like from a theoretical standpoint, you set B equal to the cache line and you're done. But clearly, from the practical perspective, there's something else going on. Yeah, thank you. Yeah. And yeah, and the reason that we're interested in longer range queries, which are not traditionally present in the original YCSB, is because they underlie new applications like analytics and graph processing, which require much longer range queries. For example, in graph processing, you often want to look over the neighbors of some node, and the neighbors may be many. So this is telling us that large nodes can improve the range scans in a traditional B tree, but you have to pay something in the point operations. And ideally, we would like to get both, that we don't want to pay anything. So this is some evaluation that we did. So we proposed to work on this data structure called BP tree. And this was in VLDB last year. This is all in memory. The way to read this is the x-axis is normalized performance. The line at 1 is BP tree. So up is good. Lower means that the other thing was slower. And the x-axis is the different workflows. So these 4 are the original YCSB. You might be familiar, like 50-50, find and insert, 95-5, find and insert, 100% find, then 95-5 short range and insert. Like YCSB A, B, C, E. And we introduced some other ones to illustrate the use case that we're trying to go for, which is longer range iteration or longer range query. So this is 100% longer range iteration and 100% longer range map. And the difference between iteration and map is the sortedness of the query. So iteration means, like traditionally in the YCSB API, it asks for, you give me some number of elements and you start at some start key. And that is totally fine, which is what we're going to call iteration. And we also identified a different kind of workload, which is map, which is that in some applications, you don't necessarily need the thing in order. Like for graph workloads, for example, you can just process you can often process the neighbors in any order, but you just need them all. Yeah, so that's how to read that. And red is BP tree, blue is just a traditional, it's like this is just some B+ tree that we got from the internet and then added optimistic, like a traditional optimistic concurrency control scheme on top of that. So there's nothing super new there, but we needed it as a starting point for this implementation anyway, so we can just keep it as a baseline. So in some sense, it's the most close comparison because the only thing that changes, like stuff stuff in the other things can change, like compiler or parallelization method or concurrency scheme, but between these red and blue, like the only thing that is different is in BP tree, what we're playing with is the node size. And like other stuff like the locking scheme is the same. So yeah, and purple is mass tree, which is a traditional indexing thing, and VW tree is also a high performance index. You see that for point operations, BP tree is either the best or close to the best. Like usually mass tree is the best in the point operations, but this is 6%, 2%, 4%. So they're not huge. So it does give a tiny bit in the point operations compared to mass tree, which is the best that we can find here for the point operations. It is better than the baseline B tree here for all the point operations.
This performance is essentially normalized latency.
This is normalized throughput.
Normalized throughput. Okay.
Yes. Yeah, this is normalized throughput. Up is good. And yeah, so you can see that the red one does improve over the blue one by trying to optimize for long range queries. And the difference becomes even more here, like in the long range operations, mass tree is down here. This is 3%. And the blue line is about 20-ish%. This is 30%. So the range queries improved a lot. And actually, compared to the B tree, the point queries also improved a little bit, which is somewhat surprising. Yeah, so that are some results. You see, yeah, so the bottom line is the BP tree matches the performance of the point operations and improves the range operations by about 1.5x. Any questions so far? Does that make sense? So this is a different way to visualize the data that we had previously. Like I was showing the plot with the 3 lines, one is range, one is find, one is insert. Just another way to do it. The y-axis is like a scatter, the y-axis is range, and the x-axis is insert throughput. And up and to the right is good. And the different points are just different points, like for different sizes of nodes. And the best one for range throughput is, of course, the biggest one. And the best one for point throughput is neither the biggest nor the smallest is 2 to the 10. And that's in bytes. 2 to the 10 is like 1024. And yeah, so there's this trade-off. This is another way to see the trade-off between point insert and range query, which is that the best case for the range queries is 2.4 times the best case for the point query, but 16x slower for the inserts. So we had to pay a lot. And you would never like care about down here because up to the right is good. The point is that there's no best node size for all the operations. If you want range queries, you should go this way. If you want point queries, you should go that way. And the goal is that we want to achieve good performance on all the operations. So to understand the reasoning, increasing the node size increases the number of elements that you access during the long range queries and reduces the number of indirections. So for example, in a long range query, let's say that you have to read these blue elements. If you have small nodes, you have to do this pointer jump to the next one. If they're connected in a B plus, in the large nodes, you don't have to do the pointer redirection. And this wasn't such a big deal when you had short ranges because maybe you had to read 2 nodes and maybe it didn't really matter that much. But if you have to read like 100 nodes, then it starts to become an issue. However, it doesn't work if you just increase the node size, because we saw this previous issue. If you have larger nodes, you have to do more work during the insertions because small nodes, like in any node, when you insert something, you have to shift stuff around to maintain the sortedness. In the small nodes, you have to shift less things. Large node, you have to shift more things to maintain the sort. And that's sort of natural. That's why the inserts are getting slower. And so we want to improve the performance up to here to overcome this trade-off. And this red line is this same experiment with the scatter plot visualization, but with BP tree. So indeed, you can see that it is in this desired green range. The inserts are about 1.5% faster, and the range queries are about 1.5x faster. And the reasoning, the high-level notation is like traditionally the B tree uses sorted arrays just in the nodes, and it doesn't have to be a sorted array, it can be anything. And there actually was a paper previously doing some experimentation in the space, like enumerating the types of possibilities that you can use in the nodes, but that was more of a, they didn't actually implement the data structure, it was just like an exploration of the space. But they did give some high-level intuition that it doesn't have to be an array. So the observation is that we should focus on the leaf data structures because every insert modifies at least one leaf, but most inserts do not go up. So it matters less what you do up here. It mostly matters what you do down here because it's the bottleneck. And all the elements appear in the loops. So you always have to touch at least one. So yeah, this is the data structure that is proposed in the BP tree, which is called a buffered partition array. And one way to think about this is that, so normally every node in your B tree has an array in it. And you can think of this as you kind of take 2 levels of the B tree and then you collapse them together into one array, where every leaf node is one chunk here now. And then you have some kind of, this is called a header that directs you where you should go. So that's like the 1 level up pivots. And then there's a buffer attached. So the thing itself is not super complicated. It's still an array, but it's just now you have to do some management. And from an implementation perspective, it's kind of like a drop-in replacement. Like if you imagine that your node data structure has some operations like insert, find, if any data structure that you implement to replace it should also support the same API like insert and find, and then you can just drop in whatever else you want to experiment. So this part is a buffer. This part is like the higher level index, 1 level up, that allows you to jump between these levels, or that allows you to jump between these segments. And then these are called blocks, and blocks are just like the leaves in the original B tree. One thing to notice is that this thing needs to be sorted because it's like a level up, but this thing and these things do not need to be sorted.
And the blocks in the sorted internally.
They don't need to be
Oh,
necessary.
you don't need.
Yeah.
Yes, yes, yes.
It does make it slightly more complicated when you do the range, when you do the iteration, if you need sortedness. But I'll mention it later. You can sort it on the fly. So here's an example. We're just going to use the same array that we had before. These are the blocks, and then we have some buffer here. So suppose that we insert this element 22 into here. We have space in the buffer, which is the log, so you don't need to do any flushing. We're just going to insert it there, and that's the end of it. However, if we insert a new thing and now this becomes full, we need to flush it. And the way that works is that you just use the pivots here, and you figure out how many things from the buffer are going into each one of the blocks. And it is fine, and the blocks have some fixed size. It is fine if they don't overflow. So this one, nothing is going here, so it's 2, that's okay. Nothing is going here, that's 0, that's okay. And 3 things are going here, and that's problematic. So, oh yeah, nothing is going here because this is an update. It's 8 already exists, but these are just unique new elements. And this is going to be 5, but the capacity is 4, so we need to do some kind of redistribution. And then we did some very straightforward thing, which is you take everything, you shove it together, you cut it up evenly, and then you redistribute it, and maybe you have new pivots. There maybe are fancier ways, like there are data structures that I will talk about in the second half that do fancier redistribution. But because these are relatively small, like at most 10K or so elements, you don't need to do, it is actually more efficient to do it this way than to do some fancier rebalancing scheme, because the fancier ones are more worth it when your data structure becomes large. So that is insertion. The more complicated, or the only other complication is when you want to iterate through the range, the blocks are not necessarily sorted, so you may have to sort them on the fly. The way that it works is first you sort the log, and then it's just like 2-finger walk. So you want, here in this example, the start key is 7, the length is 2, we want to return 2 elements starting at 7, and we have some function that we want to apply to them. So we start with the log, and we start with this pointer here. So first we would return 7, because 7 is smaller, and it fits in the range. Then we advance this pointer to the correct block. And then we see this pointer to the buffer and this pointer to the blocks. And we know we should take this one because this is more recent. Whatever's in the buffer is more recent than whatever's down there. And yeah, that's the end. We take this one. We took this one already, and we're skipping this one because it had already appeared, or it already appears in the buffer, and the buffer is more recent. And if we wanted more stuff, we would just continue this walk. But this example just has 2. Yeah, this is just some additional micro benchmarks. So the y-axis is throughput, up is good, x-axis is leaf size, and the dotted lines are BP tree, and the solid lines are just regular, or sorry, the solid lines are insert, and the, no, that is right. The solid lines are B tree, the dotted lines are BP tree, and so we should compare find and find, which are red and green. You can see that green is above red, and we should compare purple and blue. And you can see that there is some cutoff point between the two. But as node sizes get larger, the regular B tree's insert is falling off, like we saw in the beginning. And then you can do a similar thing for long range. So as expected, like if you fix the leaf size, the original B tree is of course going to be faster because with the B plus, or with the BP tree, there's some overhead, like you have to maintain the 2 pointers, and maybe you have to do some sorting. But the point is that you're never going to get leaf nodes this big in the B tree. So it's not totally fair. Like it's kind of like sometimes you would compare a B tree with a smaller node size versus a BP tree with a larger node size. But this is just to show that indeed there is some overhead, and the overhead gets wider as the scans get longer. Because like the amount of extra stuff you have to do is greater. So that's pretty much all the results on the BP tree that I want to talk about, but we can come back to this question in the beginning, which is like why, like the core of this is why are big nodes helping the range query? It seems a bit weird, like theoretically 1 cache line should be sufficient, practically maybe a few cache lines is fine. But actually it's like traditionally the node sizes are pretty small, like 256 bytes or maybe up to 1K bytes. And what is weird is that the range queries are continuing to improve, seemingly with huge nodes, like this is 64K. That is actually a bit surprising to me, that like I kind of thought it would flatten off at some point, but you do continue to get benefit up there. And one way that we can model this is with more advanced caching models. So the disk access model is the most classical model for analyzing cache line access or disk page access. And it's similar to the ideal cache model, which is another model for algorithms, but without the tall cache assumption. And in the disk access model, it's the most simple model. Every memory block fetch gets unit cost. So you have a small memory, you have an unbounded big memory, and you're counting how many blocks you have to move between them. And in this example, like we had to move these lines, and each of them cost 1. But there have been more advanced models than the DAM. More recently, there has been the affine model, which accounts for sequential block accesses, which is related to things like prefetching in memory. And in the affine model, it's similar to the DAM, except that if the blocks are contiguous, the first one costs you 1, and the subsequent ones cost you alpha, where alpha is much less than 1. So previously this cost 5, and now it would cost 1, 2, 3 plus 2 alpha. If these two are after this one. He initially did like the startup cost of getting it already. In memory, this is prefetching. In disk, this is like seek, for example. Yeah. And originally it was for disk, but you could theoretically, there's no reason that you could apply this in memory. I think this is maybe the first indexing paper that I've seen that actually tries to do something practical about this. They did have some paper doing micro benchmarks on this, but it was in disk previously. Yeah. And one way to see the BP tree is empirically is leveraging this affine model of taking advantage of contiguous access. And we can see that this affine model is true for RAM. So this is totally independent of a B tree or anything. This test is just, you have a giant array like 1G or 2G, and you cut it up into pieces and you access parts of it. And the block size is set by this x-axis. So it's just a micro benchmark, it's unrelated. And y-axis is relative time. Oh yeah, it's 8G. The blue line is the empirical performance. The green line is what is predicted by the DAM model, and the red line is what is predicted by the affine model. You can see that indeed the empirical line is matching up better with this affine model. So we can verify that in memory as well. Yeah. And to summarize this part, the BP tree overcomes this trade-off between point and range operations to optimize for both point operations and long scans. So you want to optimize for range query without giving up on point operations. The affine model is one way to determine the benefits by doing some like orthogonal micro benchmarking and then applying it into indexes. And this is the same thing from the beginning.
So what is the most important design decision for changing the shape in this code? What was the most, of all these designs, you mentioned the elements that we discussed, what was the most important thing that changed the performance?
The first step is to just make the nodes bigger, and then the second step is to save the cost of shuffling. Like the main issue with making the nodes big is that you have to do more shifting when you do the insert. So to save the cost of, you want to save the cost of shifting as much as possible. So that's the reason why there are separate blocks and header that you kind of.
So they kind of very important to the main decision.
Yeah, I think so. The first one is pretty straightforward. Just you make the nodes bigger. That's sort of. I don't see a way to improve the range query without making the nodes bigger. So that's the first part. So we did BP tree, and the second part that I want to talk about is CPMA. Yes.
Good question. So before we move on, with BP trees, I wanted to know if you manage the size of the trees or the blocks within the data structures of the block to the node size of the B tree. Performance is it similar, or do they end up like is the B tree going to be better than base?
I see. So
Yeah.
Not the entire array, but just the individual blocks.
Right, because it sounds like that's the correct mapping, right? At least in my mind, that seems to be the correct mapping, right? Like the B tree node is implemented with a block within the B tree node, right?
Yeah. I think it would be more, the B tree would be faster if you were doing that comparison, because the BP tree has some overhead, like it has to deal with the buffer and it has to find where it is it has to do the indirection, it has to do the lookup into the blocks, and it also maybe has to do some rebalancing. So, yeah, if you compare just the block size with the corresponding node size, then the node size would be faster.
Gotcha. And then everything was done in memory.
Everything is random. It would be interesting to see how to do this on disk. For the actual next step. Thank you. So the second part that I want to talk about is CPMA, which is an efficient batch set parallel set without pointers. And there's two kinds of update parallelism that we will talk about today. The first one is like the most popular one in index, like for almost all indexes, they're in this concurrent bucket, which is you have some data structure and every thread is responsible for the inserts. You can imagine the parallelization like you have a for loop over the inserts, and then you just think like a parallel for rather than the for. And you need to do some kind of locking mechanism. So that's concurrent. And blocks or lock-free data structures, either one. But the point is that like each thread is responsible for one update. And more recently, there's this alternative parallelism model, which is called batch parallel. And the way it works is that rather than every insert being one separate operation, you insert a batch of them. It's kind of like bulk loading, but usually bulk loading is from empty often. But this is from, like there may already be stuff in here and you want to add more stuff. And each batch is atomic, but the stuff inside the batch can be processed in parallel. So almost all these algorithms are based on merging, or in trees. In trees, they're based on tree merge. In arrays, they're based on array merge. So they're very different structurally from the concurrent data structures. And there is more, from like an implementation standpoint, these usually scale much better because you don't have to deal with the locking overhead. I see this as like you trade latency for throughput. Like you increase the latency because maybe you have to wait for the batch to fill up, however you got your stream. But once you get a sufficiently large batch, you can apply it really fast because you don't need to take blocks. Because often the main bottleneck here is not like the actual insert cost, it's the contention or the locking mechanism. And the insert is finished when the whole batch is finished. So that's what I'm saying, like you are increasing the latency, but the throughput is very fast once you have the batch. And these have become really popular in dynamic graphs, especially because you get like a batch of edges and then you apply the thing, and they usually phase the edges. They usually phase the inserts in the algorithms. So like you can't do reads while you do this, but you can apply the inserts very fast and then you do the algorithms after that. So the second half is in the batch part. And sometimes they call these like lock-free algorithms, which is like technically true, but I don't think it's totally fair because it's not really like a traditional compare and swap based lock-free algorithm. It's just you don't have any concurrent writers, so obviously you don't need locks. Anyway, so this is batch parallel data structures, and to date, almost all of them are based on pointer-based things like trees, B-trees, skip lists, pointer things. And pointer data structures, batch or concurrent or whatever it is, are usually very fast to update, like they reach the lower bound for updates in the DAM model, but they are relatively slower to scan than arrays, because of course, reading contiguous memory is faster than reading pointers, even if the block size is like, we just saw in BP tree, even if the block size was 1K, it's still faster to read an array. So this is a cartoon. X-axis is batch update performance, y-axis is range queries. And packed memory array, which is I will teach you more about it later. This is an array-based dynamic data structure, is up here. It is very good on range queries, but previously there was no batch algorithm for them. So of course the batch algorithm is nothing. And then packed trees, which are a very fast implementation of batch trees. The batch update performance is out here, but the range query performance is relatively worse compared to array. And the goal again, we want to be up into the right. So in PPoPP this year, we introduced this packed memory array using batching. And one interesting thing about this is that these, from a theoretical standpoint, you might not ever really care because they are worse for inserts from a worst case amortized perspective, and the range queries are asymptotically equal to B trees. But practically the range queries are better if you read an array. And the idea is that we want to do batching. And like I said, the high level way that all these algorithms work is through merging. So a packed memory array is this thing. It is cache oblivious, which is maybe interesting. So cache oblivious means you don't need any cache parameters to tune the thing. So like with a B tree, it is not cache oblivious because the parameter B depends on something related to the memory block, ideally. But here, the setup is cache oblivious, which means that it does not depend on the cache parameters. It's just an array. If you have n elements, this thing is size theta n, where you have some empty spaces in between. So like blue is the actual elements and white is the empty space. And it's cut up implicitly into leaves. They're called PMA leaves. And each leaf is size log n, theta log n. So log n has no dependency on B. But you can still prove bounds in terms of B, it's just not in the actual setup. And the actual most interesting thing about this is that it is one giant memory allocation. This memory allocation defines an implicit binary tree on top of the leaves. So each leaf is a block of size log n. And this tree is never actually realized, but it's just the way that you search or interact with it, which is that it's kind of like how you can think of just a regular array as an implicit binary tree if you do a binary search in it. But now this is blocks rather than something totally packed together, and the tree tells you how you should search through the entire thing. And this tree also tells you how you should maintain the empty spaces. So every level has some density bound, where density is the number of allowed slots that are filled in each segment. And every parent or like every internal node is just every node in its subtree. So like this one would be these two, and this one would be these four. So yeah, and the density range gets stricter as you go up. And this is what I'm talking. This is what I was mentioning a little bit earlier. Like there are array-based things with fancier rebalancing schemes, and this is of course much fancier than what we had in BP tree, which is like you just when one block is full, you totally rebalance the entire thing. Here's like if this was full, but if this had enough space, then you would just rebalance these two. We actually tried to put this in the BP array at first, but it turned out that the overhead of maintaining this thing was too high. So like we traded range for point, and that's not what we wanted. And the way that searching works is you start from the middle leaf, you just do a binary search on the first element of each leaf. And once you reach the correct leaf, then you scan through the elements to look for the thing that you wanted. The search is something like log n cache misses, which you can see is already worse than B trees, which are log base B of n in the LeapDem model. And inserting into the PMA is like this. You first search for where the element goes. So here, for example, we're trying to insert 22. You first search for it. It goes between 19 and 89. You put it there too. And here in this example, the density bound is 0.9. So this is not right because the density is 1, and that's higher than 0.9. So we need to find some neighbor that has enough space that can take the elements. Here, there happens to be enough space, like this is 0.5. If you added one here, it becomes 0.75. And then this is now 0.75, 0.75. And you can see this is like rebalancing. And there's some theory about this. It turns out that the worst, in an amortized sense, the worst case is like log squared, actually, which is even more than a log factor off of features. But that's in a very worst case distribution. So doesn't always realize the worst case bound. To do the parallel batch inserts, it follows the insert algorithm sort of closely, which is that first you have to you get a batch as your input. You have to merge the elements into the array. You count the nodes, which is in this previous step, we had to count this part to see which nodes really need to be rebalanced and which ones can be rebalanced into. And then the last one is once you find the nodes, you just redistribute them. That part is really easy. You put them together, you cut up evenly, and then you sort it out again. So these two are maybe the most complicated parts. So this is an example. Here's the PMA, and here's the batch. And the colors are which node they're going to go into. So these tan ones, 2, 3, 4 are going to go in here. 7, 8 going to go in there. 11, 12, 13 will go in here. And 16 will go in there. And the way this works is through divide and conquer. So you search for the midpoint, you pick the midpoint of the batch. Here it's 8, you just pick the median. And this is already sorted, actually, so that's important. This needs to already be sorted. It could be a pre-processing step as well, like if your batch does not come in sorted, you have to sort it. And yeah, then you search for this midpoint in here, and that tells you which leaf it's going to go into. You find the beginning of that leaf, you can just walk left. Then you merge. So 7 and 8 get merged into here in sorted order. So now 6, 7, 8, 9. And now you have, this now defines 2 halves, like this half and that half. And you just do some recursion on the 2 halves. So now this is done. You have merged everything in here that is going to be merged in. And now this left half is 2 through 4, this right half is 11 through 16. And you just do the same thing again. And this also divides the PMA into 2 halves. And it's just the same. And this is fine. The only small trouble is that sometimes you don't have enough space in your leaf. And natural way to fix it is, so here, like suppose this was the leaf, 1, 5, and 2 empty spaces, and we want to put 3 things in, then we store everything out of place. And this is a special value, tell you that stuff is out of place. This is how many things are out of place, and this is a pointer. But of course, we cannot leave it like this. In the end, it has to be resolved back in. One reason that this is good, even on one thread, this is good because it saves a lot of the searches that you have to do. So in the concurrent parallelism, even if 2 elements are going to the same leaf, both still have to traverse top to the bottom. And actually it causes a problem because in concurrent setting, like both of them now need the same lock, which is an issue. But here in the batch world, it's much easier because if multiple elements go to the same leaf, you kind of like save the search. You only have to do 1 search per leaf in some sense. And all of the elements that are going to that leaf, you can just determine them once you have found that leaf and you just look left and right, but you don't have to do another top-down search, which is a huge benefit, even if you ignore the parallelism for a second. The parallelism comes pretty straightforward, which is like I said, you recurse on the 2 halves, both those halves are independent. Yeah, so some elements can come out of place, redistributes have to fix those, and in the paper, which is I'm not going to talk about it now because it's not worth the time that it takes to explain, which is that actually doing the counting in parallel is a bit tricky to get right efficiently from a theoretical standpoint. From a practical standpoint, actually counting is very fast. So it's just a theory thing. Actually. So here's some data. The batch inserts, the y-axis is insertion throughput, the serial line is here, which is blue, and the parallel line is here, which is red. And even on one thread, you can see, oh yeah, x-axis is batch size, which is just, that's the input. You see, we saw 2.5x speed up even on one thread because of this, you can save the work. And on 128 hyperthreads, we saw about 47x speed up over serial point, which is here. However, like if you compare this one and this one, this is only about 20x on 128 threads, which is not ideal.
The whole red line is on 64, sorry, is on 128 threads.
Yes.
Okay.
Yes. All points here are on 128 threads. Okay. The only thing that changes is the batch size. Thank you. Yes. So we want to fix this because 20x speed up on 128 threads is fine. It's not great. But you can see that like these throughputs are really high. It's natural that as the batch size gets bigger, the throughput is going up because you share more work. But these things are hard. This kind of speed up is a bit hard to see in concurrent data structures because this does not have any locking overhead. So a natural trick when you have, the whole thing is memory bound. A natural trick when the thing is memory bound is you add compression. So this blue line is without compression. This red line is with compression. And you can see that the scaling is indeed getting better. So here, this is strong scaling with cores. Physical cores up to 64, and then 64 hyperthreads. The red line goes above 40. The blue line is kind of less than 20. And then similar, so that one is insert, this one is range query. Range query is much better because it doesn't have any writes. So range square you can see is even, it's like perfect scaling almost, it's going up over 100. And blue is less than 50.
What do you mean by compression here?
Good question. Yes. So compression is the most simple delta compression possible. It's using bytecodes, which are like you do delta compression and then you store bytes, like one signal bit and then 7 bits of payload. So it would be interesting, like if there are more fancier compression schemes. This is like as simple as it will get. But maintaining compression dynamically is a bit challenging. This is just saying scaling is good, throughput also increases, not as much as the scaling, of course, but throughput went up 2x with compression for inserts in the biggest batch. Throughput goes up 1.3x on the largest batch with range. Yeah. Finally, this is compared to baseline, so everything else so far has been internal, and we do indeed want to verify that this is an improvement over trees. The trees are already quite fast, actually. So blue is the PMA, red is a compressed compressed batch tree, and yellow is a batch binary tree. You can see actually the binary tree does quite well on inserts, but on range, it kind of falls off because this thing is memory bound. And the blue line is higher than both trees, which is actually unexpected and not according to theory, but because the reasoning for this is that the theory is sort of similar to the story in BP tree, which is that the theory does not account for contiguous memory access. Usually you just count single block moves. And of course, this thing is going to do more than that, but it does more contiguous block moves, which is the reason that this line is higher. And yeah, this is what this is naturally expected, which is that arrays are faster to scan than trees, but in the limit, they are getting closer. The node size in here is actually like 4K, it's pretty big. So to wrap up this section, despite the theory, CPMAs can again overcome this trade-off between updates and scan. This is like a similar story to the concurrent, but it's with PMAs. And these results are promising, but there's still a way to go because trees are like this very classical data structure. There's so much going on in them besides just throughput, like or latency. There's like snapshots, persistence, disk-based version, which is all missing in PMAs. So it'd be interesting to see whether this improvement can translate once you add this additional functionality. And this is the same cartoon as in the beginning. And I spent a week on this doing the artifact, and we won the best artifact. It's so hard. You just have to like, the vibes are like, if you've ever played Factorio, the vibes are like hooking up all the pieces and automating the thing end to end. Yeah, so that's the end of CPMA. Questions? So really quickly to wrap up, the common thread between these two are cache optimized designs. So in BP tree, it was optimizing the array in the leaves to be bigger. And in CPMA, it's optimizing the entire thing to be one giant array. And both of those are just cache-friendly designs that can and we show that optimizing for the cache, you can overcome the traditional trade-off between point and range operations. And the reasoning for that is because it is fast to access large blocks of memory. So from a practical perspective, accessing these large blocks, even beyond a page size like we saw in BP tree, can still benefit you. And yeah, that's it. Thank you.